Hey everyone. In this video, I'm going to talk about causal inference with unobserved confounders. Okay, so in the previous video, we talked about strategies for causal inference that basically assume conditional ignorability of exposure or treatment assignment after adjusting for all potential confounding variables. Okay, but oftentimes that is just not a realistic assumption, right? Oftentimes we just cannot, or in most cases, essentially, we cannot be confident that we have measured all potential confounders, okay? So what we're going to do in this video is explore or give a brief overview of a couple of alternative causal inference strategies that basically rely on slightly different sets of assumptions where we can basically make causal inferences even if we have unobserved confounders that may impact both treatment assignment and the potential outcomes themselves. Okay. And the first kind of strategy or inferential strategy that falls into this category is instrumental variable estimation. The idea behind instrumental variables is that even if ignorability of the treatment assignment is unlikely to hold, right? So we don't have this, so that the treatment assignment is not ignorable. There may exist another variable that does appear to be randomly assigned or can be considered as such. Okay, and if this variable that is exogenous, that is basically randomly or quasi-randomly assigned, is predictive of our treatment itself, then we can use it as an instrument and ultimately use it to estimate causal effects of the treatment using a model that is called two-stage least squares. Okay, the idea behind two-stage least squares is basically that we have two sets of regressions or two sets of equations where on the one hand we're basically modeling our treatment assignment as a function of our instrument, okay, and that instrument again is exogenous. We can assume ignorability of the instrument itself. One example that you've seen quite a lot, for example, in the economics literature, is to use rainfall as an instrument for a whole range of other outcomes that are endogenous, like GDP or conflict and things like that. And we'll talk in a second about why that is problematic as well, because it's predictive of a lot of different things. But the point is that it's exogenous, right? It's not. It's randomly assigned, whether it rains or not, or where it rains. At least in the context or in a certain regional area, can be assumed to be exogenous, can be assumed to be essentially random, right? And so we use that to predict the treatment itself, and then use the predictions of our treatment as a new independent variable in our outcome regression to predict our outcome of interest. Okay, and basically by isolating a certain kind of portion of the variance in our treatment variable or our treatment measure that is basically just predicted by our instrument, we can then basically isolate a certain causal estimate for the treatment effect. Okay, there are a couple of important assumptions that we have to make in this instrumental variable design. The first assumption, of course, is the ignorability of the instrument. So even if the treatment itself is not ignorable, there are potential confounding factors with respect that are correlated with the treatment and correlated with the outcome. The instrument itself has to be ignorable, right? So something like rainfall or other potential exogenous factors would work. But as soon as the instrument is not ignorable itself, then we basically lose the advantage that we gain, and instrumental variable estimation doesn't really make a whole lot of sense anymore. Okay. So basically, in the absence of like a controlled experiment, for example, where we have an encouragement design or some type of natural experiment, this property may be difficult to satisfy and may also require conditioning on other pre-treatment variables or potential confounders. Okay, and as I mentioned, to the extent that this assumption is difficult to justify in our instrumental variable context, basically any advantage over a traditional observational study where we're relying on the ignorability of the treatment assignment mechanism itself is basically lost. Okay, so this is a crucial assumption that the instrument itself has to be ignorable. Okay, then we have to assume monotonicity, which basically means that we have to assume that there are well, to explain this, we have to kind of step back and talk a little bit about different types of compliance and how people respond to the treatment. Okay, so essentially, when we have a treatment, we can think of 4 different types of reactions to that treatment. Okay, on the one hand, people can be basically responsive to the treatment if they're assigned to the treatment condition. For example, encouraged to watch a certain or read a certain article. They can comply with that treatment assignment. So they read the article if they're in the treatment group, and they don't read the article if they're in the control group. We can also have always takers. Those are people who basically always take the treatment, regardless of whether they were assigned to the treatment group or to the control group. So those are people who always read the article in this example, regardless of whether they're assigned to the treatment group or control group. And never takers, who never read the article, never take the treatment, regardless of what group they're assigned to. Okay, and then there's a 4th group, which are defiers, which basically do always the opposite of the treatment assignment. So if they're assigned to the treatment, they basically take the control, so they don't read the article in our framing experiment, for example. And if they're assigned to the control, then they do the opposite and they read the article. They take the treatment, right? And so the monotonicity assumption basically requires that there are no defiers. Okay. So we're defining, we're basically saying that there are only either compliers, never takers, or always takers, but there are no defiers. There are no people who basically just only do the opposite of what they're encouraged to do by the treatment. Okay, in many applications that is plausible to make this assumptions, but of course you can probably come up with examples where that might not be so realistic. Okay. The third assumption is non-zero association between the instrument and the treatment variable. So the instrument needs to be predictive of our treatment. Otherwise, we have a weak instruments, and if we have a weak instruments, so those that are not strongly predictive of the treatment, then we have potentially we induce bias, and we are highly vulnerable to violations also of the exclusion restriction. Speaking of the exclusion restriction, that's the 4th assumption, and that is kind of related to this rainfall example that I mentioned. The exclusion restriction basically states that the instrument should only affect the treatment assignment, but not have a direct effect on the outcome. Or in other words, it should only affect the outcome through the treatment assignment itself. Okay, so for example, I mentioned this case of rainfall, which is often used in political economy and political science research as an exogenous instrument. But the problem is that it's used as an exogenous instrument for a lot of different things. And if it's used for a lot of different things, or if it is predictive of a lot of different things, then essentially what this means is that the exclusion restriction doesn't hold. So that means that it's not the case that this instrument only impacts a certain outcome through a specific treatment, like conflict or GDP or something like that, because the instrument also impacts other potential kind of mediators that ultimately then impact the outcome as well, right? So as soon as that doesn't hold, then we cannot use the instrument, or this will bias basically our inferences. Okay, so the exclusion restriction is very very important as well. A couple of other assumptions that we talked about in the past also have to hold, for example, non-interference or SUDVA, but those are not specific to instrumental variable estimation. Those are kind of more general to kind of inference that we talked about in the past. But if those assumptions hold, we can basically use our instrument to predict our treatment variable, and then use those predicted values of our treatment value in the second stage equation to then get a valid estimate of our complier average causal effect. So a key thing to keep in mind here is if we use instrumental variable estimation, we're not computing, or we're not estimating average treatment effects anymore, basically average treatment effects across the entire sample, but rather complier average causal effects, which means we're looking at basically the effect of the treatment on the subset of the population that complied with the treatment, so they actually followed the treatment, right? So basically removing always takers and never takers. For those, we basically cannot we cannot estimate treatment effects based on this instrumental variable estimation. Okay. This is usually compared in kind of IV analysis. This is usually compared to the intention to treat effect. The intention to treat effect is basically the effect of being assigned to the treatment, whether or not the respondent then actually took the treatment or not. Okay, so this is the basic effect that you can always estimate if you have, for example, an encouragement design where you encourage people to, read a news article or watch a certain program. And some of them might do it, some of them might not do it. The intention to treat effect is basically the effect of encouraging people to do it, not the effect of the actual exposure, right? And the complier average causal effect that you estimate using two-stage least squares is then the effect of the actual exposure, but only for those who comply basically with the treatment assignment, so only among compliers. Okay. So that's the brief overview of instrumental variable estimation. The next strategy that I want to talk about is the regression discontinuity design. The basic idea with the regression discontinuity design is that we basically have some mechanism of assigning treatments based on some continuous running variable. Okay. You can, the kind of canonical example of this is think about admission to certain educational programs or universities based on a test score. And if you pass a certain threshold, if you have a certain minimum score, you get accepted. And if you don't, then you don't. Then you're not accepted to the program. Okay. The point here is that if we want to estimate the effect of this particular program, then we can basically compare units that are very close to either side of the cutoff to ultimately estimate the treatment effect of that program itself. Okay, so units are treated on one side of a threshold or cutoff and not on the other side. Okay, so that's the treatment mechanism, and the threshold is determined using a continuous running variable, for example, a test score in the context of admission to a program. So that means that units very near the cutoff are considered similar except for their treatment status. Okay, and in a case like that, we can basically in the simplest specification, but this is not usually how it would be specified in actual published research. We could basically run a regression with the eligibility, so whether you're basically above the threshold or not above the threshold, as one covariate. Sorry, I mislabeled these, and basically the underlying continuous running variable as an additional covariate. Okay, and so let's see, maybe let's look at this first. So we have an underlying assignment variable. This is continuous, basically, right? This could be the test score. in our for our admission to the program, and then we have a threshold. Anyone above that threshold will be admitted to the program. Anyone below that threshold will not be admitted to the program. And so the kind of idea behind the regression discontinuity design is that observations that fall just below the threshold and just above the threshold are comparable, are basically, the treatment is ignorable for observations that are very close to that threshold. And so we can estimate the effect of the intervention or being admitted to the program based on a comparison basically within a bandwidth below the threshold and above the threshold. Okay. One way in this particular specification, we're just basically estimating or fitting a regression line without an interaction, so with equal constant slopes on both sides, and we have an intercept shift for the for observations that are above the threshold versus observations that are below the threshold. In usual, like in most standard applications, we would probably include some kind of nonlinear function for the assignment variable. So some polynomials, for example, to take into account possible nonlinear relationships between the assignment and the outcome. And potentially also look at interactions. So we have different slopes, or alternatively look for interactions. So we have different slopes on the left-hand side and on the right-hand side. But the point is that ultimately we will then estimate the treatment effect at this threshold, basically. There are two important assumptions to keep in mind. Again, the first one is that the probability of treatment is determined by this threshold. Okay, so we need to have some mechanism of treatment assignment that is known, that is based on some continuous measure. Okay, this can be deterministic. Then we have what is called a sharp regression discontinuity design. Or this might be also changing continuously, which would imply a fuzzy regression discontinuity design, which is slightly where we need kind of like additional steps to kind of estimate the treatment effects then. Okay, but the underlying idea is always that units sufficiently close to the threshold only vary meaningfully in their probability of receiving the treatment. And therefore, we can basically assume that within a certain bandwidth across the threshold, the units are comparable, or in other words, treatment assignment is ignorable, and so we can estimate treatment effects by comparing those groups. However, and again, this is kind of similar to the methods that we talked about previously, the average treatment effect here is only tells us something about units that are close to the threshold. Okay, so this is again a local average treatment effect, not across the entire sample, but only basically for observations that are close to this threshold. For any other observations far away from the thresholds, we cannot really make any statements about their treatment effects. Any statements that we could make would be strongly determined by our modeling assumptions of how the treatment effect or how the potential outcomes are related to the assignment variable itself. Okay. And again, this is just a broad idea. Of course, there are a lot of questions regarding how we model this relationship between the assignment variable and the outcome, how wide this bandwidth is that we should include, how many observations we want to include, and obviously there is a trade-off here between kind of having a larger set of observations, but then on the other hand to have this kind of assumption of ignorability within that threshold or within that bandwidth to be met. And so there are a lot of important choices regarding bandwidth modeling and so on that you'll have to dig into if you want to use regression discontinuity designs in your own research. Okay. Now the last set of kind of strategies for causal inference with observational data are based on leveraging variation or studying variation within or between groups. Okay, and the first one that I just want to briefly mention is based on panel models or panel data using fixed effects models. or varying intercept models as an alternative. And the basic idea is, if we have panel data with repeated observations within groups, basically analyzing panel data can provide a means for adjusting for unobserved characteristics of these groups. Okay, so by basically looking at here a basic fixed effects regression, where we include a varying intercept for each of those groups, and we're looking at the effect of a treatment within that varies basically within each group. Okay, we can basically account for all confounding factors that might influence both treatment assignment and the outcome on the group level. Okay. The key thing to keep in mind here is that the causal predictor here needs to vary within group. If it doesn't vary within group, we cannot estimate it, because we're controlling for a group level, or we basically include group level fixed effects. And we can only account for unobserved characteristics of these groups that are basically constant within group. Okay, so in that sense, we can account for some unobserved confounders, but it's certainly limited to only factors, basically group level factors in this fixed effects specification. Another very common technique for causal inference with observational data that we already covered a lot in 702 in our last semester is actually difference in differences. So just as a very quick reminder, the basic idea of difference in difference is to compare the change in an outcome in treated units before and after receiving the treatment to the change in the outcome in untreated units over the same time period. And we can model this in a regression framework basically by including both an indicator of the treatment as well as an indicator of the time period prior to treatment or receiving the treatment or not, and then the interaction between those two. There's a little plus that is missing here. And basically the interaction term is then the difference in difference estimator. Basically the change in the slope over time between the treated group and the control group. There are important assumptions related to that as well, and we talked about those in the last semester. The crucial one here is the parallel trends assumption, which basically implies that both the treated and the control group, at least in terms of their potential outcomes, were on the same trajectory. So, in other words, that we're assuming that if the treated group hadn't received the treatment, the trajectory, the change in the outcome would have been kind of equivalent to the trajectory or the change in the outcome that we observed in the control group. Okay, which is obviously an assumption that might be or is oftentimes more plausible than a pure observational comparison, but might not apply in every specific instance. Okay. So this was a lot of different models. I just wanted to kind of cover a lot of different strategies, so you kind of have an idea of what the underlying principle is, the underlying ideas are, and then again, if you if you're working with data that are where you could apply one strategy versus another strategy, make sure to check out those kind of additional readings to dig more deeply into the material and be able to use those techniques in your own research for your dissertation and so on, right? But what I wanted to achieve here is just give you a brief overview so you know kind of what the strategies are that are out there, and then we can also in the Q&A session talk a little bit more about each and every one of those in detail, depending on your substantive interest and depending on what is most useful for your own research. Okay. In general, just for a conclusion, causal inference with observational data is incredibly challenging, is very, very hard, and it requires strong assumptions, right? We're not only just talking about predictive inferences on comparisons between groups. If we want to actually estimate a causal effect, we need more assumptions than basically the simple sets of assumptions that we talked about initially when we talked about predictive comparisons. Okay. And in general, it always helps when you try, even if you have observational data and you want to make causal inferences, it always helps to kind of think about hypothetical experimental data that you could have, in an ideal world without any constraints, that you could have collected, and kind of think about the different potential outcomes and think about the comparisons that you want to make, and then kind of think about how you can kind of translate that into or recover kind of some of that variation in the context of your observational data. Okay, there are a lot of different considerations that we have to take into account. Temporal ordering of the measured confounders of our treatment indicator, of our outcomes in the context of observational studies, that make this a lot more difficult than, if we actually run an experiment. Okay. Another thing that is really important to keep in mind is that it is very difficult to interpret more than one input variable causally in any observational study, right? So if we have a large regression with a lot of different predictors, it is oftentimes a fallacy to kind of think that the model is correctly specified so we can interpret all of the coefficients causally, right? That is not the case. What we have to do is focus on one input, one variable that we want to where we want to where we want to estimate a causal effect, and then think about exactly what specification is needed in order to estimate that specific causal effect, right? And that implies including a certain set of confounders and so on, but interpreting those confounders then causally would be wrong, right? Because in order to identify the causal effect of those confounders themselves, we basically have to go through a whole different kind of set of arguments, thinking about what confounders are and exactly how we can identify causal effects, right? So when you think about causal inference, it's always about identifying a causal effect of one input and setting up the model specification to identify as best as possible, correcting for confounding factors for that specific input. We never talk about causal inference for the entire model with all predictors that are included in the model. Okay, and so ultimately, kind of this type of reasoning where we kind of focus on all coefficients and interpret them all causally, and the underlying issues with that are kind of related to this distinction that we kind of came back to again and again, both last semester and at the beginning of this semester. Which is this difference between searching for the causes of effects versus the effects of causes, right? And so oftentimes when we think about theory and think about the questions that we're interested in, we're starting with a certain puzzle and we're ultimately searching for causes of effects, right? We see a certain anomaly, we see a certain pattern, and we're thinking, okay, what causes this pattern, right? But that's not how we think about causal inference. Or at least that's not how those are not the types of questions that the causal inference methods that we covered can actually answer. The causal inference methods that we talked about, they're about estimating effects of causes. So identifying a specific input, identifying a specific cause, and making sure that we can estimate the effect that this intervention has on a specific outcome of interest, right? So in that sense, causes of effects can be very or thinking about causes of effects can be very useful from kind of a theoretical perspective for hypothesis generation, potentially for model checking. But ultimately, when we engage in causal inference, we're focused on estimating effects of causes. We select one specific input, one specific intervention that we're interested in from a theoretical perspective, and then we set up a model that best helps us to identify and estimate the effect of that particular cause, right? So as you continue in your work using quantitative methods and work with observational studies, and kind of think about the theories that you want to test in your in your work, make sure to kind of think about framing the actual analysis that you want to engage in as examining effects of causes versus kind of this question of causes of effects. What caused that anomaly, that puzzle that you're ultimately interested in, right? Both are related, obviously, in your theoretical reasoning. But ultimately, when we talk about causal inference, we're estimating effects of causes, and that's really important to kind of keep in mind. And with that, I'm gonna wrap it up. This was the last video for 702. I'm looking forward to our last Q&A session, and I'll talk to you on Monday.